Hi everyone, welcome to this last lab in this semester for the AES algorithm. Um, so in this design, we're gonna have two types of implementation. The first one is pipeline, second one is iterative one. So the basic difference between them is a pipeline have, as you can see, they have more hardware's utilization here, but in general, for the large amount of the data, it should be able to have a higher throughput. All right. Um, the mathematical details is already introduced in the lectures, so the block diagram is summarized into these slides. So we're dealing with the 128 versions. All right. So what are we gonna do is just run these two implementations and check the source code and do some analysis. That will be it. So the code already provided to you here. Just download them and open in Vivado here. All right. We will go over this pipeline design first. So as you can see, we have this top, we have this test bench, and the main part is implemented in this AES pipeline design here. And so under this, there are many submodules in this hierarchical ways. All right. So if you want to check the hierarchy conveniently, you can open this elaborated design, click on schematic. You should be able to see the hierarchy of this. All right. This is the AES top design. So here we basically have three parts here. So on the left, this is the input. On the right, this is the output. All right. We have this PLL generating a stable clock design for the, generating a stable clock for the whole design. We have this VIO. VIO is it's like a oscilloscope within Vivado, right? It has a lot of probes connecting with the design so that you can see the real-time values of them within the Vivado. And also we have this main part in this design. If you double click into this, you can see the details. The details basically summarized in this diagram. All right, we have the input as a plain text. We have the output as a ciphertext, right? So these correspond to this. Okay, we have clock, we have reset, we have the key input, we have the plain text input, we have the ciphertext output, and we also have this valid signal to tell the module if or say when they are getting ready, and we have this valid out in the same idea, right? These are the parameters. You should be already familiar with this. Just data width and the number of rounds, right? So in total, we have the very first round key operation, and then we have 9 rounds of this substitution, shifting, and mixed column and round key operations in a row. And lastly, we have some final 3 operations here, and we have the output. So this corresponds to the code. Basically, they are matching very well. All right. So here, this is the very first round key operations, and here we have the generation of the, let's see, the 9 rounds of the round here. One round of this is just 1, 2, 3, 4. This 4 operation in a row. This is a round here, right? If you click into this, as you can see, we have the sub bytes. We have shift rows, mixed columns, and round key operations. All right. So this is just a round, and after this 9 rounds, we have the final sub keys, shift rows, and round key. And we have this connecting to the output ciphertext here, right? This is the same as this part. So yeah, so if you want to see this in more hierarchical way, you just click on this schematic and click into this. You should be able to see. So on the very left, we have this add run key for the very first time. We have run 0, run 1, run 2, and 2 here. We have run 8, and these are the last operations here. All right. And we also have this key expansion. This is to provide provide a key for each iteration here. Okay. So the key is stored, right? Or say the key is saved into this W. And we also have this valid signal, right? So if you click on this, you should be able to see the key is connected to each round through this highlighted wire, right? Until the last round here, and this very last round key. Okay, so this is just one way to see the hierarchical schematic here. Let me see. Yeah, so I think this is the code here. So once you get familiar with this, you can run a simulation. All right. So this is a simulation. It's called the pipeline design here. We have two rounds of, or say two different inputs. The key are the same, always the same. All right. So 0, 0, 0, 1, 0, 2, 0, 3, until 0, 5, 0, F. But we have two different data in here in different timing for the input. And if you have everything running correctly, you should be able to see the result here and here. All right. First one is 9486 and E356. Let's check the. Where is my simulation? It's gone, so I'll just run it again. Oh, sorry. Here we go. We have so if you don't see, maybe you only see some top signals. If you are this, you can right click on this, click on add to window so that they show up here again. All right, and you click on this run again, it will just run again and show everything here. All right. So this is a cloud, as you can see. This is very dense. Let's go to the very first. As you can see, let's zoom in a little bit. Okay, as you can see, we have the input. Where are the input? Data. Okay. Data in. This is the input here. All right. This is the first input, and this is the first output. 9486. So that should be matching with this, right? And yeah. So later on, we have the second round starting from here, but here we only analysis the first round. As you can see, there are basically 10 rounds here. As you can see here, 1, 2, 4, 8, 10, 20, but these are hexadecimal numbers, right? They are not actually 10 and 20, but they are 4080 zeros. But as you can see, there are some data run here. As you can see, the data out in each round is getting valid at this timing. All right. So within this, you can using this to analyze the throughput of your design. All right. For example, our input is valid at let's just count the rising edges. Okay. So the input is getting ready at this clock edges, and the output is ready at these edges, right? So you should be able to know how many clock cycle is between the input and the output. And this is how you calculate the throughput. The definition of the throughput is how many data can you process per second. Okay. So here you should be able to know how many clock cycles it requires to process the data for once. And also you know that given the PLL we have, and given the PLL, our design is running at 200 megahertz, right? Using these numbers, you should be able to calculate the throughput. Okay. If you see the simulation is all right, you can move on to run the implementation here. Somehow this is I'll discard this. Somehow this is, I think it's already been run previously. Okay, I have the implementation complete. So if you open the implementation design here, you should see this is a chip, right? This is, as you can see, all the utilized blocks here. You should also see some report. For example, if you click on report, you can report the timing summaries, you can report utilization, you can report power here. They are all here. All right. Yeah. So this is how you get familiar with your design. For example, here we have power 0.3 watts, and most of them they are dynamic power, and we have the static power is only take like 24%. This is okay. All right. Your shop will also take care of the utilization. Let's see. Let's run one utilization here. So you have a general idea of how many resources is included in this, for example. So as we all know that this FPGA basically contains LUTs, flops, IOs, and also it should be able to contain the DSPs and RAMs, but we don't use them in this design. So we only have the LUTs and flops. These numbers are something we really care about, okay? For example, here, the utilization of the LUTs and flops, they are 60%, 73%. This is relatively a high utilization compared with the iterative design. So in general, you will have the most dense design you will have is around 60 or 70. If it's over 80, it's sometimes really hard for the routing. And yeah, so we don't want to have that high utilization. Anyway, take a screenshot of this, including the report. Okay, let me know you actually check this. All right. Let me see what else. So the requirement for you is, okay, you should also check after this, you will generate the bit stream, all right? Once you generate the bit stream, you will connect the board directly with the computer where you have this Vivado running, and follow the instruction here, instantiate VIO. I guess it's already done for you here, but you want to make sure the configuration is as as here, right? Double check the configuration here. And then you will download the bitstream into the board, and after that, click on Open Hardware Manager, and you can click on Open Target, and the Vivado should be able to automatically detect the board connecting to the computer. All right, it will just run in real time and modify some input. So I would recommend just use input here. All right, the key and the data in already provided for you. Just copy and paste into Vivado and running in the real time. You should be able to see the real time output using this VIO as instructed here. As you can see here, we have the data in here, and you should be able to see the data out within Vivado. Take a screenshot of this, all right? Include in your report. So this is only required for the pipeline design, right? This is only for the pipeline design. For the iterative design, it looks like we have some timing issues. I don't know how to resolve this, so you just I won't require this for you, but you just check the run a simulation here again. All right. So the timing here is a little bit different, but yeah, so it's different. Just do this again. All right. Take a screenshot of this. And also another issue I have found is that sometimes so you should be able to run the implementation successfully without any errors, but in some cases you probably have a when you click on the generate bitstream, you probably have some errors. Let me see. I don't have it here, but I have it previously. Something like something specified about the output port temp output. If you have it like this, I would recommend just open this constraint file here and copy and paste the last two T codes and click paste it here, hit enter, and this should solve this errors. All right, just generate again, and you should be able to move on. Yeah, I think basically that's it. Just I will modify this. All right, so for the implementation, you should only do the pipeline design, but you can skip this iterative one. All right, but you want to report the power utilization of the whole design. And also, let me see what else. Oh, throughput is calculated by the way I told you before, right? And you want to do some analysis. And the latency is another metric to check your design, right? The latency is just the number of cycles between your input and output. Here, for example, I don't have the. I will just skip it. I think you should be able to figure that out, right? Yeah, I think for this time it's relatively easy one. You just download and run everything, right? So good luck on this. I hope everybody can finish it on Tuesday. And thank you everyone for this whole semesters. If you have any suggestions on the lab or any feedback you wanna give me, just let me know. If you can, there should be a feedback system on Canvas, but you're also welcome to post it on Piazza or directly email me. All right, it's very actually I had a good time with you in the lab session, so I actually very enjoy them. Thank you all. Thank you all for this, and hope you good luck in your future. right? Thank you. Bye.